Hello. Hariharan. Naresh, can you hear me? You can reply by the way of questions. Great. Great. So, all right. So, good morning, everyone. Let's start the session. And feel free to ask as many questions as you want using the questions window. All right. So, a little bit of instructions. The session is being recorded. So, and recorded video will be shared with all of you along with the presentation. So you don't have to worry about taking notes all the time. But feel free to take the notes if you want, and feel free to blog about us in case you want. If you want to summarize it on your tech blog, that's all right. And in this session, you can ask questions by typing. Only I am unmuted. Okay. So before we introduce the other things, let me introduce you. We have Naresh from Bangalore, who is working as admin and AWS Cloud. Good, good. What about others? Feel free to introduce yourself using questions window. All right, so a little bit brief about No Big Data. No Big Data has tries to have the instructors as expert as possible. Our focus is on bringing the subject expert in the instructor who are from product development industry, not the typical trainer industry, mostly the basically the product development guys. And we have something called cloud labs. Using cloud labs you can connect and learn any of the Hadoop ecosystem product along with the MongoDB and Spark and R. Everything is installed on the cluster, so you don't have to struggle all the time with installing stuff on your machine, because sometimes you're working on office machine, sometimes you're working from home, so it becomes very difficult to work on any big data systems this way. That is why we have set up a central machine servers on which you can connect and learn. And the other reason behind setting up cloud labs is most of the components which we train in are related to big data. And all the components in big data runs on multiple machines simultaneously. That is why it is important to know how does a component feels. It is important to know how does a component feel. So how does it work when it in on running on multiple machines simultaneously. The third reason behind cloud labs is typically what people do is they generally install virtual machine and they start working on it. That is mostly for experimentation purpose. But in an organization, wherever you work in real life, you basically have a central cloud setup where all the tools are installed, and that's where you run your program. So cloud labs gives you the more real time feeling of learning the technology. All right, we have Rajgopal, who is a UI developer and data science enthusiast. Great to have you, Rajgopal, in the session. Now, all right. We also provide you, when if you sign up, we provide you the lifetime access to the LMS so that in future you can come back and revise all the videos, presentation, assignments, and quizzes will be available to you in the future date also. And whenever we have a new complimentary course, we generally send an email to all our students saying that we have got a free complimentary course. Along with that, we keep on improving the course, and you will have the new set of recordings also available for future courses. If you perform good in our sessions, then we give you a real life project, and there is a course completion certificate which we give it to our candidates, which is online as well as on the social networks. We provide you a 24 by 7 support via email. And in case the problem is difficult to debug, we generally have a online hangout session where we can see your screen as well as we can see our servers on which you are working. All right. And we have built a group called No Big Data Alumni where we post jobs. We we keep on sending you complimentary sessions and updated content, and we connect you with the other alumni of No Big Data. All right. So feel free to ask as many as questions you want. Okay. I would love to answer. All right. So I'm Sandeep Giri. I did my graduation in 2002, around 12, 13 years ago, from IT Roorkee. And then I worked for an interesting company called DE Shaw. There, even though the world did not call it big data that time, we were working on big data, meaning a 10,000 nodes cluster and the data in 100 terabytes. That's what we were working at Deisha. And after that, we were working. I started a company called T-Bits Global. It's a product company which built our document management system like Documentum, and lots of large organizations use it for building power plants. After that, I joined InMobi and Amazon. At both the places, I worked on building the big data systems for for them. Right? In 2014, last year, around 1 year ago, we started this company called No Big Data, along with few of my friends, and we have been trying to build the best possible way of training people, best possible way of making people learn and making the learning interesting. Okay, so I enjoy training. I enjoy explaining complex things, and I love technology. That is why this no big data. All right. Now that is about me. So today we are going to learn what is big data and the Hadoop architecture. All right. Before we move forward, do you have any questions for me? Yes. All right. So no questions. Moving on. So feel free to interrupt and ask question. Okay. And uh, I mean, as and when the question comes to you, you just type it instead of waiting for me to stop and answer. Okay, so just type the question and I'll answer um, whenever a slide ends or my sentence ends. Great. So today we are going to discuss these topics: why, what, and why of big data, why now, and then example customers, what is Hadoop, and then components of Hadoop, architecture, and then name node and data node. All right. Okay. So here we go. Before I start, let me ask you a very simple question. What do you understand by big data as of today? What is it that you understand by big data as of today? Yes. So Naresh says that it is data in massive size. What about others? Large volumes of data, that is Bhargav. Any other? So you can answer using questions window, okay, by typing. Hariharan says it's processing huge amount of data, unstructured big amount of data. That is Rakesh. Anybody else? All right. So yes, you guys are right. A big data is basically the data of very big size which you cannot process with usual tools, right? Which you can't process with usual tools. And now out of this, all right. So big data means the data of very big size that you cannot process with usual tools, and data could be structured or unstructured or semi-structured. What does it mean by structured? When in the data you know exactly what fields are there and what is the data type of each fields. For example, a database table, you know exactly what are the fields, as in what are the columns, and what is their data type. So that is structured. Unstructured is when you don't know the fields in the input data clearly, and for understanding the data you might have to parse the data and convert the strings into individual integer, long, or boolean, or whatever data type it is. So that kind of data, when you don't know what are the fields and what are their data types, you generally call it unstructured data. For example, an Apache log, where you have a huge plain text file containing logs that need to be parsed in order to do the computation of anything. Okay, in order to process it, in order to do any kind of you know churning, you have to parse such kind of data, understand which field is where, what is the data. That is unstructured data. And there's something called semi-structured data. Semi-structured means you know the fields but you don't know their data types. For example, a CSV is semi-structured data. Hi Prabhat, welcome to the session. Now feel free to ask questions as and when you want. So whenever we talk about big data, we generally talk about something more important than the size. And basically when you define big data, usually you say the data of very big size that you cannot process with usual tools, and this data could be structured or unstructured or semi structured. So as you can see that first point, data of very big size does not mean much. You might ask, how big? Does it mean 1 terabyte? Does it mean 100 terabyte? Or does it mean 1 gigabyte? Right? And second point, cannot process with usual tools. What does it mean by usual tools? Okay. Third is structured and unstructured, which essentially means all kinds of data. Right? So the most important part of this definition is distributed architecture required. So as a general thumb rule, when you cannot handle your data using usual tools and you require a distributed architecture system, what does it mean by distributed architecture? A system which runs parallelly on multiple machines to solve your problem. That is a distributed architecture. Okay. So if for a data of huge size or because of some other reason, if you end up having a distributed architecture, that means you are dealing with big data. So your data could have huge volume, data could have huge velocity, data could have huge variety or veracity. What does it mean by volume? The data which is stored is of huge size. For example, terabytes of data which is already there in your hard disk. That is the volume. Okay. The velocity means the data in motion. For example, your website would be receiving thousands of requests per minute. And this request which the website is receiving is termed as velocity. There are cases where there's a humongous amount of velocity, but there is no volume accumulated. Okay. One such case is your website counter. When the website counter just increases the number by one, although website counter might be hitting the server at least thousands of times. Okay. If there are more users, it would be hitting the server many times. So the velocity is there, but volume is not there because it's just increasing a number, a counter, right? So by virtue of the motion of the data, we might end up with big data because one single machine may not be able to handle that kind of request, and hence a distributed architecture would be required to handle such circumstances. Therefore, when we define big data, we define it as it might be due to velocity, it might be due to volume, it might be due to variety, and it might be due to veracity. How it is due to the variety? So imagine this, you have a huge Google Maps or huge maps data, and this maps data is in the form of geospatial form, as in you know the coordinates of various things, roads, and all kinds of traffic data. And Even though the volume of this data might be say 100 gigabyte, but to process such kind of data, it will take humongous time if you try to do it on a single machine. You might have to have a distributed architecture in order to process such kind of data. And therefore, the variety, the kind of data you are processing makes it a big data if you end up having a distributed architecture. Okay, so the variety might lead to a heavy load, and hence we might call it that because of this characteristic called variety of the data, we are having big data problem. All right. Then the fourth one is interesting. Fourth one is veracity. Although it looks pretty redundant, and it looks more like something IBM wanted to do just to add one more V to the definition. Okay, and they are adding one V every year. Okay, but nevertheless, let's define what is veracity. The data in doubt. At lot of times, you end up having lot of data because you are unsure whether this data is useful or this data is useless. Okay, so because of incompleteness, ambiguities, latencies, model approximations, your data might be useless or may be useful, but you don't know yet, and hence you have to handle the data till the point you reach to a conclusion that this data is complete waste of time, we can throw it away. Till that point of time you need to handle it. Okay, so because of this you might end up having a lot of data lying around, and hence you might end up with a big data problem. Okay, so take a practical case. Imagine that you have temperature data of the whole globe. Imagine this. You have the temperature data of whole globe, as in the in Fahrenheit or centigrades. So, and you got the temperature data from various kinds of sources. So first source gives you the data with respect to each each GPS coordinate around the world, and it gives you per second data. Second data source gives you the the temperature in every zip code, and temperature in every zip code as well in every minute. And there is third data which gives you the temperature in any other form, at any other points of time and any other points of coordinates. Now you have got these three data sets, each of say few GBs in size. Which one to keep and which one to disregard will be a big question. So you will have to do a lot of processing in order to reach to a conclusion which data you can throw away and which data you can keep. Okay. And till that point of time, till the time you reach, there is a confusion that out of these three data sets, maybe all three are useless or maybe more than one is useful. And till the point you reach to a conclusion, you have to store it, you have to process it, and hence you will have thrice volume of the data. And because of this thrice volume, you might end up with the circumstance that you need a distributed architecture. Okay, and hence we call that, because of veracity, because of this confusion on which data to keep, which data to discard, we have the big data problem at hand. So is it clear to all? The volume, velocity, veracity, and variety. These are the four characteristics of the data. First three characteristics are basic, and fourth is just extension. All right, so just to check whether you are awake or with me, how many bytes are there in a petabyte? Yes, 1024 gigabytes. That is terabytes, Hariharan. Okay, Rajgopal says 1024 terabytes. Naresh says 10 per 15. Great, great. So, yes, your answers are right. The answer is 10 to the power 15. All right. And the better way to remember it is kilo mega giga terabita, and each one is 1024 times the previous one. Okay. So, mega is 1024 times kilo, and so on. All right. Now, so you know what is a big data? Big data is something for which you require a distributed computing, or you can say a data to for which you require multiple computers to solve the problem. So storing 1 petabyte data is a big data problem or a small data problem. Yes. So we know what is big data and we know what is petabyte. Petabyte is something having 15 zeros, or you can think of 1000 hard disks is what you need to store 1 petabyte data. So my question to you is, does storing 1 petabyte data a big data problem or not? Sham says not necessary. Anybody else? Rakesh says storing is not, but processing is. High volume. Prabhat says yes. Okay. Naresh says yes, it is. It needs to computation. All right. So even for the storage, whenever you want to store 1 petabyte data, to store it reliably, you would have to have a distributed architecture. In no way you can store 1 petabyte on a single machine. Even if you stored 1 petabyte on a single machine, somehow you will not be able to read the data at a faster pace. Okay. So, although it's impossible to store 1 petabyte data on a single machine, you cannot connect 1000 hard disks on a single machine. Secondly, for having a reliable mechanism for 1 petabyte data, you might have to have a backup of this one on another one. And there are other reasons why you would like to go for a distributed architecture when it comes to the data of 1 petabyte size. All right. So yes, 1 petabyte is 1 petabyte is a big data. Almost all the systems cannot handle it. Okay, cannot store it as well as handle it. And of course, for computation of any kind, if you want to even do a simple summation or average of some value out of this 1 petabyte data, it is going to take a lots and lots of time for a single system to do anything on this data. All right. This is a typical diagram which shows you that The digital storage has expanded exponentially after 2002. So after 2002, the digital storage, the lower part is the digital storage, the upper part is analog storage. And analog storage is something like paper, film, audio tape, etc. While digital storage is your hard disk, CD, and etc. So as per this graph, this is up to 2007. The data was only 280 exabyte in 2000, and an exabyte is 18 zero. Okay, exabyte is essentially 1024 petabyte, and which is 18 zeros. So in 2007 itself, the data was 3 into 10 power 20, which is huge. And also, the important part is that data was increasing exponentially. In 2002, the explosion happens, the data started expanding suddenly. Okay, Shyam's question is, so if one of the four characteristics is fulfilled, we can say it is big data. Yeah. So if because of one of the four characteristics, you have you have to have a distributed architecture, then we call it a big data, right? Because every data has got volume, every data has got variety. So those four characteristics alone are not sufficient to say something is a big data. The most important part is for any problem with respect to data, if you require distributed architecture, you call it a big data. You call the data as big data. All right. So in 2002, we mark it as beginning of the digital age. And why is it so? In 2002, two things started happening. First, the devices, and second is the connectivity. You got smartphones, and other devices which are basically the generators of the data. And then you got this internet connectivity which has been improving every day. And in this because of the connectivity, this data gets multiplied across the internet. For example, as I'm talking right now, I'm uploading, I will be uploading 1 gigabyte of the data in these 3 hours. Okay. And say there are 50 members attending this session. There are 50 members attending this session. The 50 GB data will get transmitted from GoToWebinar server to the people. So because of the internet or the connectivity, the data gets multiplied. Okay. And because of the great devices as of today, like I have some laptop. I'm sorry, let me just turn off my phone. Okay. So because of the connectivity, the data gets multiplied, and because of the devices, like we have phones, we have computers which generate a lot of data. And we have sensors across the world now. We have cameras, and there are a lot of devices which are basically generating a lot of data. So while connectivity improved after 2000s, and devices became cheaper, faster, and smaller. So cheaper, faster, and smaller, these are the three criteria which every hardware manufacturer follows, and they have been doing it religiously, and that has resulted in this whole generation of data, um, a lot, right? So while on one hand the devices have become cheaper, faster, and smaller, connectivity also has become cheaper and faster. So Naresh's question is, so any vast data with distributed architecture is big data. Yes, exactly. All right. So we just discussed two things: connectivity and devices, which led to the big data explosion. Now, why is a big data problem? Okay. So most of people think that if we have big data in terabytes and petabyte, we have great big processor which has four cores and can handle anything you throw upon it. Okay, so let's understand that it's not only the processor which matters. There are other components which are the pillars of computing. The four pillars of computing, or the four components that matter for the computing whenever you want to do any kind of processing, these are the four things that you require, or that you would require at one point of time or the another. Okay, so first one is CPU, which we all know. Second is RAM. And when we say RAM, the two characteristics of RAM, the size and the speed at which the CPU can read the data from it. Okay. The third one is disk, the size of the disk and speed of the disk. You have solid state hard drives which have high speeds but small size. You have normal magnetic hard drives which are slow and unreliable, but they have got humongous size and they are less costly. Okay. And the fourth one is the network connectivity. All right. That matters a lot when you are dealing with big data. So if you have very small data and you have to process it, you can just load it in the RAM. And when I say RAM, it means all sorts of random access memory. It might be a L2 cache, L1 cache, or it might be registers. Okay. So RAM is something on which you load the data to get it processed. So when you have small data, you just load it in the RAM and process it. But as the data grows, you this data needs to be spilled over to the disk in order to be processed properly. I- Imagine few terabytes of data you want to sort. You cannot load this 2 terabytes of data into the memory in order to process it. Most of the data structures schools only taught us how to do stuff when the data is in the memory. Okay. But in the real life, as the data has is growing bigger and bigger, you cannot accommodate it in the memory. And whenever you are dealing with any kind of systems in real life, RAM is the one which becomes bottleneck first. In case of a Wikipedia, the only reason they had to load balance and run it on multiple computers was because the RAM became the bottleneck in the machine. So any web server, first thing that hits is the RAM. CPU is generally free. All right. Now the second part, which after you start spilling the data onto the disk, you start now your disk will start becoming the bottleneck. If your data is few hundred terabytes, then you cannot store it in disk. Then you will start spilling it over to the network. And the moment you start spilling over to the other computers, then the network becomes the bottleneck. So when you are handling the big data problem, at least one of these will become an impossible bottleneck. Okay. At least one of these four components will become an impossible bottleneck to solve without introducing one more computer. And the moment you introduce one more computer, all these four things have got doubled. You got one more processor, you got one more RAM, you got one more disk, and you got one more network. So effectively, you have doubled your capacity from all angles. All right. So these are the four things which you need to keep in mind. And when you engineer anything, you will be basically shifting the load from one of these four pillars to another one. So if your disk speed is slow, then and your RAM is available, you put cache in place. And in case your RAM is getting full again and again, you spill it over to the disk. And in case you are not able to fit it in the disk, you move it to the network, and so on. All right. Now let me give you a few examples of big data customers where the big data really matters. The first one is recommendation engine. A recommendation engine is something like Amazon's. Let me have a look at. All right. So the recommendation engine could be of various forms. The first one to use recommendation engine was probably Amazon. Although recommendation engine is a million years thing, we have been recommending things to each other since forever. Okay. Okay. So, but recommendation became interesting when the data grew bigger because then the recommendation really meant a lot because there's so much of data, and hence preparing a proper recommendation will be more closer to the reality than you get the recommendation in using few data points. Okay. So the recommendation could be that you may also like this. People who bought this also bought this, and you can wear this particular thing with these things, and there could be complete the set kind of thing that if since you are buying these two things, you can add one more item and you will complete the box. And similarly, the movie recommendation is quite something which has become recently popular after Netflix organized a contest. All right. So based on your behavior, the recommendations are given to you. Okay. So a general way is we understand what are the movies do you like, and then we do it for all the people, say hundreds of thousands of people. We do it, we gather what are the movies they like and how much they like each movie, and after that we try to figure out of this data who are the people who are similar in the taste, and then we try to do a cross recommendation. So if I and Prabhat are very similar to each other, or I, Prabhat, and Naresh, all three have more common movies than the difference, then it is easier to give the recommendation to each other. All right. So a very quick and rash way of telling you that how can you do the recommendation is, say you prepare a list of movies and who are the people who like it. Say Kumar likes this much, and you prepare this kind of a list and you feed it to a solution called Mahat, and Mahat will give you the proper recommendation. Okay. So this is how you quickly do the recommendation. If you have to do it in next half an hour, this is how you will do. All right. So recommendation was first problem to be tackled with big data because the more the data, the better the recommendation gets. Okay. Second was the sentiment analysis. So in the recent times, during elections and cricket matches, it would be very important to figure out which campaign is working good, which campaign is not working good. Okay, so such kind of analysis, meaning understanding what is it that is working and what is it that's not working, is done via something called sentiment analysis. Understanding what is the mood of people, what's the general mood of people, and and this is basically very very important in today's times. A general way of doing it is download all the data related to me, related to your brand. Say you are launching a product called laptop, or let's say you are launching a product called no big data. Okay, now you want to understand how is your campaign going, how is the people responding to it. So for your keyword, you download all the tweets from Twitter. That's just for one way. You download all the tweets from the Twitter, and once you have downloaded all the tweets, what you do next is you try to understand what does each tweet say, whether a tweet is negative or a tweet is positive. Okay, a quicker way to do it is, for each word we find out whether a word is negative or positive based on a dictionary, and then sum up the sentiment of each word. After that, if the whole string is odd, that means it's negative. If it's even, then it's positive. So we give odd number to a negative keyword, and a even number to a positive one, and then sum it up, assuming that a negative and a positive keyword makes up a negative, and negative and negative makes up a positive, and so on. This way we compute the sentiment of a tweet, and we do it for all of the tweets. So at the end of the exercise, we know uh, in which country what is the sentiment, negative and positive, about your brand. So as part of our big data course, these two problems which we will discuss in detail when we go into this one is by the end of the session. So So this one is the first session which we conducted for free out of our 11 sessions. And in the 11th session, we will discuss the sentiment analysis. And in the ninth session, we will discuss the recommendation engine. All right. There are some more big data customers such as government and healthcare and life sciences. Okay. And there are telecommunications companies like Vodafone and Airtel. Telecommunications company like Airtel and Vodafone. And they use the big data to avoid the customers leaving them, optimize the network performance in order to cater to more users and give a better experience. And calling data record analysis is something which we do to understand the behavior of users, as in what time people call more, and what can we do in order to increase the experience. Fourth is analyzing network to predict failure. This is something a lot of people are working on. Other than telecommunications, few use cases with respect to government is identification of fraud, and detecting a fraud is a difficult scenario. The only way you could do is by observing the pattern in fraud, and the other use cases are healthcare industry. All right. Any questions till now? Hello. So any questions till now? So these are few example big data customers. There are many more. These are just few examples. Okay. All right. So this diagram, this basically a slide which shows how many instances of Hadoop is being used by who. And the bigger the font, the more are the number of Hadoop instances which are in production. All right. So here are few common myths which go around in the industry. First one is big data always means the data above or in range of terabytes. Okay, that's not true. As I gave you an example of variety where you had 200 GB of Google Maps, which you need to analyze in order to reach to some output. Okay, so I will talk about Hadoop. Hadoop is Prabhat's question is what is Hadoop? Hadoop is one of the solutions to process big data, process and store big data. Okay, we will discuss in the second half. Just give me a minute. Just give me a minute. All right. So these are the common 11 myths about big data. First one is the it's always to do with 1 terabytes of data. That's not true because even if your data is smaller, such as example I gave about the maps data, for which the computation is heavy, you might end up having I mean the distributed architecture even if you have 100 GB data. All right. So the first one is the myth for this reason. Second is big data is always about social media and doesn't apply to me. Okay. So the answer is no because as of today, as I was telling you that there are so many devices available and so many devices are generating data, whether it's sensors, whether it's cameras, there's a lot of data which is being gathered, right? So it is not only to do with social media. It is just up to you how closely you look at your organization, how closely you look at your problem, and you will realize that a lot of data is available to you as well. It's just that you are ignoring it. It will replace enterprise data warehousing. The answer is no. It will not replace enterprise data warehousing because because enterprise data warehousing handles a relational data pretty well. A smaller but very structured way of handling data. So big data solutions will not replace EDW. They will basically they will basically coexist. Second, it's just a buzzword, no practical application. That's not true. The I've seen almost every organization I have worked with, there was one or two big use cases of big data. In case of Amazon, the whole thing runs on big data. And in case of InMobi, the moment they started handling the data properly, and they started having the clusters of Hadoop, they were pretty successful. So, is a new concept. It's just a new name for a old concept. As I was telling that at DE shop we had humongous data which we used to churn. So, and we had similar systems like Hadoop, but not that polished as Hadoop at DE shop. So it's not definitely a new concept. It has been there for last 30 years. It's just that now, since more and more devices has come in, more and more data is being generated and the connectivity is available to everyone, therefore it has become useful to everyone now. Will be the future? No, it is the present. Is expensive? The answer is no. Almost all the big data solutions, sophisticated big data solutions, are available for free in open source. Okay. And most of them are Apache license, which makes them useful even in the enterprise world. Is only for data scientists or is magic? So it's not only for data scientists, because though the example I gave about recommendation and sentiment analysis, the there is a small role of data scientists. For example, understanding a full sentence using a natural language processor is something data scientists will do for you. While you can utilize those algorithms in your problem solving easily, and that's where the role of data science scientist and your role starts. So it's not only for data scientists provide some algorithm, you can utilize them to build really useful systems, and it's not definitely a magic. As in this diagram, I showed you something very quickly called Mahat is an algorithm provider which takes an input and gives you the output. The algorithms in Mahat are written by various data scientists and you can use them. So it's no longer a magic. Ninth is we have got enough hardware. So big data is nothing to do with hardware. Okay. The almost all the solutions under big data are built such that they can utilize existing hardware to the maximum possible. Okay, all the big data solution can utilize the existing available hardware to a very large extent. And and as and when you can start building your big data solution using few computers, and as and when the load is growing, you can keep on adding computers to this solution. Okay, this is called scaling up. Sorry, scaling out. This is called scaling out. And and almost all the solutions which come up today, they come up with a system that you can keep adding the hardware or removing the hardware without changing any configuration. All right, so it's not about hardware, and we will build it when we need it. This is probably the most fatal myth which people live with. Okay, the problem with this statement is that people think that they will build it when they need it. The truth is they will only need it when they really build the basic of storage. Those who say that we will build it when we need it, they don't build a good enough storage, and hence their developers in those organizations, the developers keep on removing the data, compressing the data, ignoring the data, and hence they never gather enough of the data to process. And effectively, they they don't find a use case because they don't have data, so they don't come to a relevant use case of utilizing data to do any kind of prediction. So effectively they end up with no with the situation that at a later point of time, when they realize that they need to build some big data solution, they could develop this kind of insight or that kind of insight, they will realize that they don't have any data stored. Therefore, it is strongly recommended to lots of people to build a huge storage and give the comfort to the developers, to the various people in organization, to keep the data about customer, about other products in place in order to take the maximum benefit out of it. Okay, so big data is about Hadoop. Hadoop is just one solution, it's not everything. Okay, Hadoop is just one solution. All right, so all right. So, and regarding job, lots of people have this question about jobs. There are a lot of jobs in big data. Even recent Forbes article, actually top 3 points were regarding big data, and as well as Gartner. And at the same time, the if you look at Naukri.com and Indeed.com, although this data is little older, you will see that there are a lot of jobs. And most important thing you might notice is the big data jobs as of today are high paying jobs, which means that the competition is less in this domain as of today. Okay. Now, what are the various big data solutions available as of today? One of the most common and most complete is Apache Hadoop, which we will discuss today. And then is Apache Spark, which is only for doing computation, not for storage. Then is Cassandra. Cassandra is a database which helps you do a lot of processing as well as storage on some sort of structured data. So MongoDB is another one. Both of Cassandra and MongoDB are considered as NoSQL, but they don't compare with Hadoop because Hadoop also has a file system and also has a lot of machinery for computation and data import export. And then there is something called Google Compute Engine. Google Compute Engine is a hosted solution. In case you don't want to build your own infrastructure, you can utilize Google Compute Engine. Google Compute Engine also provides you a Hadoop kind of library. Shyam's question is Java knowledge important to learn big data? The answer is no. So in this course, which we give a training upon big data and Hadoop, we give you a training of about 13 components. And out of 13 components, only for one portion called map reduce, a little bit of any programming language is required. We have tried our best to avoid Java programming language, but we make sure that you learn MapReduce even without knowing Java. All right. So for this course per se, the Java programming language is not really required, but knowledge about any programming language, even if you have done programming around 10 years ago, it's okay. You'll be able to handle it. And in general, if you are getting into big data domain, you don't generally require knowledge about Java programming, but you would require a little bit knowledge about any programming language. And moreover, we give the recorded videos of our Java programming session to all our students as complimentary. How easy or difficult it is for mainframe COBOL programmer to pick up big data? It's fairly easy. Okay, there have been many candidates in our class from COBOL and mainframe background. They did pretty well. All right. Now they did pretty good in our sessions. All right. So, first question that comes into my mind: what is big data? What is Hadoop? After we have discussed about big data, we discussed about big data as in data for which we require distributed computing, and there are many use cases of having big data. There are reasons why most of the existing solutions don't suffice all those four pillars, and we also discussed the other solutions available for handling big data. And out of all the solutions, Hadoop is probably the most complete one to handle big data. So, what exactly is Hadoop? Hadoop was created by a person called Dog Cutting along with Mike Caffarella. They were building Nudge search engine project. They were building a search engine like Google called Nudge for their in the personal time while working at Yahoo. He named it after the toy elephant, and basically it is based on the paper by Google. Okay, based on based on Google file system, Google MapReduce. Okay, okay, Google MapReduce and Google Bigtable. Okay, so while these people were trying to build their own search engine, they realized that the uh, you know, existing file system or database are not sufficing. So at the same time, Google published these papers and they realized that this is what they need in order to build a system which can store a lot of data and which can process a lot of data parallelly. All right. So and it is for reliable, scalable, and distributed programming and written in Java. Right. Now, so it started with two, three components such as a file system and MapReduce and HBase. File system is based on Google file system. MapReduce is based on the MapReduce is based on Google MapReduce paper, and HBase is based on Google Bigtable. So they started with these three components as part of Hadoop, but slowly they have built a full ecosystem of components, the full suite of components. So Hadoop as of today is this. It contains so many components. It starts with a file system. File system is like your C colon, D colon. Okay. Basically, it looks to you like a typical file system in which there are folders and files. You put files and you delete files, and you download a file. But beneath the hood, it is utilizing multiple computers simultaneously. Okay, so that is Hadoop distributed file system. So let's discuss a little bit about what is Hadoop distributed file system. All right. Now, my question to you is, if you have 100 terabyte of data, how would you store it? Anybody? Imagine this, that you are in a living in a hostel, and you all of you decide that you will have a central way of storing data. You will build a movie storage for all the people in that hostel, and in the hostel there are maybe 1,000 people, and you want to build this kind of a solution. How will you build this 100 terabyte of storage system? Anyone? Okay, Felix says that we'll store it in multiple machines, in 10 machines. Good. Anybody else? The maximum available hard disk as of today in the market is 2 terabyte. Yes. So Hariharan says LVM with all the disks NFS mounted. Good. So LVM is Linux Volume Manager, right? And Felix says then 50 plus machines. All right. Those are very good answers. So this is what we typically did. As Hariharan says, this is what we typically did. So we took these hard drives, say 100 hard drives, each of 1 terabyte size. We connected to multiple computers and made these hard drives available by the way of networking to all the computers. Now we mounted all these hard drives as subfolders, okay, yeah, under a folder. So whenever people connect to this computer and see, uh, the user will see there are 100 subfolders in which they can store the data. So drive one folder represent the first drive, second folder represent the second drive, and so on. Now, so you got 100 subfolders representing 100 hard disks, okay, and each hard disk is 1 terabyte. So what exactly do you see the problem in this architecture? Do you see any problem with this architecture? We will not utilize all the disk space. That is good. That is good. Any other problems do you see with this architecture? Okay, that was Hariharan. Basically, what he's saying that in one day, if we have allotted, there are many problems with the uniform distribution. We'll talk about it. Let me see what all other answers are there. Felix says if any hard disk failure, then we will lose the data. That is very good. That is very good. So Felix says that because of the drive failure, we will have the problem. So instead of doing that, what we'll do is we'll put one more hard disk under it, which means we'll have 200 terabyte of storage. But the second hard drive is just a backup of the first one. On each computer we add one more hard disk as the backup of existing hard disk. Okay, Shyam's question is access speed and no indexing. Very good, Shyam. So no indexes as in there is no index right now to find out which movie is stored on which hard drive. Okay. So maybe we have built a plan saying all the movies starting with A go to drive 1, all the movies starting with B go to drive 2, and all the movies starting with C go to drive 3. The problem with that approach where we are allotting one alphabet to one drive would be that all the there would be too many movies starting with A but too few movies starting with B. Alright? Similarly, the movies starting with the as in THE, there will be too many movies while there will be too few movies starting with Q. So we'll have to create sort of an index saying these are the movies stored on drive 1, these are the movies stored on drive 2, and so on. Any other problems do you see with this approach? All right. So the other problems which I see is you have already mentioned. What about failures? All right. What about failures? In case one drive fails, can another drive takes its place immediately? Okay. Second is how would you distribute the data uniformly? One drive might be absolutely full while other drives are empty. Is this value for money? Are we utilizing the resources properly? We bought these costly 1 terabyte hard disk. Maybe we already have 500 GB hard disk in our organization, and if we go to like 200 GB hard disk, we will have more and more complexity. What about increasing accessibility? This is something very important. Now imagine this: a new movie comes in and we store it on drive number 7, and we announce that a new movie has come in and everybody wants to watch the same movie, so everybody is trying to access the drive number 7, and hard disk drive is uh, will become your bottleneck, and effectively none of the people will be able to watch a movie because that might make the device so busy that it might get damaged. Okay, so the availability is not there right now. Okay, while all the computers are very free and this computer is unnecessarily too busy to cater to all the requests. So can we solve such kind of problem? The next problem with this is scaling out. As in when we are adding more machine to this network, to this kind of architecture, it will be very difficult and it will be too much of manual intervention required to utilize or rebalance the data existing on this network. We might have to change our plan, of which we might have to change our strategy of storing movies. Okay, because we might have designated already that movies starting with A will go to drive A and drive 2 and so on. So we'll have to change that strategy, right? So in the to solve all of these kind of solutions is we started they built something called Hadoop distributed file system. It solves all these problems beautifully, which is related to huge data and huge demand. Okay, huge volume and huge velocity. Okay, so let's take a break of 10 minutes and come back at 9:30. So, can we start now? Is everybody back? Great. So, Prabhat is back. Everybody else is back? All right, let's start. All right, so we were discussing about how would you store 100 terabyte data. How would you store 100 terabyte data? So, and we discussed that there were limitations to the traditional approaches which we have been using for in last decade, and those limitations were many. All right. So, for exactly those problems, we used HDFS. All right. So, for these reasons, exactly the HDFS was designed. Okay. So, as part of HDFS, you have got something called name node and you have got something called data nodes. There is a single name node and there are other data node. So it's a typical master slave kind of architecture. There is master which is called name node or admin node, and there are many data nodes. So in every distributed architecture of HDFS, it's not a single computer. These are multiple computers. Okay, these are multiple computers containing different kind of to two different kind of things. On out of the in this cluster there will be one machine which will be running a name node, and rest of the machines will be running something called a data node process. Although these are basically computer programs or processes which are running on these machines, you can run them, although you can run them on the same machine, but it does not make much sense to run all of these things on a single machine. Okay, the main objective is to utilize multiple machines to divide your data in order to achieve a large scalability. So you have got data nodes and you have got name node. A name node stores the metadata, as in the information about what are the folders, what is the what is the metadata, such as what are the permissions on the file names, what are the names of the file. All of this information is stored in the admin node. Okay, the actual data, the content of each file is stored on data nodes. Okay, as somebody was saying that there has to be, you have to have something called index. So the role of admin node is sort of an index. Okay, index which tells you where is what data. Like in a typical file system, FAT32, or any typical file system, the initial few bytes or few kilobytes know have the information about the files. Okay, exactly in the same fashion, you have admin node, a separate computer containing only the metadata, while there are hundreds of data nodes storing the actual content inside the file. Okay, so this is a typical architecture of HDFS. Now, furthermore, the data nodes which are there like this contain the blocks of 128 MB. So each file which you want to store, say it's a movie, 1 GB movie, it will get divided into 8 blocks, each of 128 MB, and those blocks will be stored here. Okay. So basically the objective of slicing the file into small blocks is such that so that you can fit a big file into smaller disk. It leaves less space in the disk and it optimizes the transfer. Okay, it optimizes the transfer between the data nodes and between the admin node too. Also, it also makes it possible to distribute the load onto multiple machines. We'll talk about these in detail. Okay, so it's it is very obvious that if you slice the file into small pieces, it will fit better. It will leave less space in each of the data node. Like if you have a big jar, if you try to put bigger pieces, it will leave more spaces. But if you cut them into small slices, then it will leave less space. All right. Now, the next is that each block which we created after slicing a big file is replicated to 3, meaning each block will have 3 copies on different machines. So a block 1 will have 2 more copies on other machines, such that in case one machine dies, still there is a block left and you can again replicate it to a level 3 to a 3 replication factor level, and then you can start then and then again it is good for fault tolerance. All right, so basically replication factor makes it possible to have the fault tolerance in place, as well as in case a read request is coming for a block, and so the read request can go to 3 servers for each block. And so if there is a 1 GB file, it has got 8 blocks, and each 8 blocks are replicated twice more, which means there are 24 blocks, and these 24 blocks will be distributed across the cluster. And when a request is coming for a file, out of these 24 blocks, 8 blocks will be retrieved. Effectively, you will be using more computers to cater to a request as compared to our earlier design, in which there was only one computer used for accessing for providing the data, right? So this makes it possible to build a very high fault tolerant system as well as highly reliable system for storing the files. Okay, so say a person one comes to visit a movie, watch a movie. So first 128 MB will be served from first computer, second 128 MB will be served from the second computer, and so on. All right. So does it make sense to you? So in case one of the data nodes, say the first data node goes down, all the data that got lost here will be quickly replicated to another data node so that replication factor of each block that got lost is again brought back to 3. The moment a block is deleted, the moment a data node goes down, the replication factor of the blocks which got lost has come down to 2. And to rebalance that replication factor to 3, another data node will get the copy of the same blocks, and again whatever was lost as part of data node will be again available. All right. So sounds good to you? Feel free to ask the questions. So no questions. Either I am really a great teacher or I'm really pretty bad teacher. All right. So Rakesh's question is this 3 default? So 3 is by default, is the default number. You can decrease or increase it per file. Okay. Similarly, 128 MB is just one, default value for the blocks. You can decrease or increase it. Is it admin node that recognizes which node has failed? Yes. So that is Shyam's question. Very good question. So admin node keeps a track of which data nodes are alive, which nodes are dead, and basically each data node keeps on pinging back to admin node. In case admin node does not receive a ping from a data node for some time, it assumes that to be dead. All right. Any other questions? Okay. Rakesh says that Hope admin node has also a redundant pair. That's a very good point. Yes, it does. Okay. We'll talk about it in a minute. Now, a typical architecture, the way we have always studied. Yes. So I'm coming to Shyam and Sanjay's question. Don't worry, I'll repeat it. All right. So in typical structure, this is how we built our systems. User comes here. So let me take up another diagram. All right. So typically, this is how we built the system. User used to come to a master, and then master used to get the data from data node and then give it to the user. As you can see clearly in this kind of architecture, the name node kind of master will become the bottleneck. But in case of HDFS, that is not the case. The general design is the client or the client library comes to name node. So, so client or client library comes to name node, and name node gives back the data, gives back the information that hey, don't bother me, just go and talk to data node. All right. So that actual reads of data directly happen between the client and the data nodes. Okay. The general reads of the data happen between client and. So there is a client which you are going to use. It might be a command line client or might be a programmatic library. All right. So this client goes to name node, and name node gives it the data that where is your file located. Okay. And then the client directly goes to the data node and reads the data. So if you have 1 GB movie, and similarly for writes, let me show you the next diagram. This is a little uglier diagram, as you can see. Yes, Sham, I'm coming to your point. All right. Now, now the next question is, in these all circumstances, the name node looks like, first, name node is not the bottleneck anymore. Name node keeps all the metadata, as in which file, which folder contains which files, and which file has got how many blocks, and which block is located on which data node. So this information is with name node. So whenever you want to read or write the data, you first go to name node, explain to it the situation what you want to do, and accordingly name node guides you the correct set of data nodes. And then you start talking directly to the data node. When I say you means the client library you are going using. A client, maybe a command line, maybe a Unix command, or maybe any other command which is representing you to read the data. Okay, so that client is going to directly talk to data node and start reading it, and for this it doesn't have to come through name node. The data doesn't have to come through name node. All right. Now it's very obvious that what if name node goes down? So first, name node tries to defend against heavy load. So nobody can overload name node. It tries to delegate things to all others. For example, when one data node goes down, the data has to copy it between the other data nodes so that the replication factor is recovered. To do that, name node doesn't read the data and writes to another data node. All it does is it informs both the data nodes to start copying the data amongst themselves. Okay, that is the role of name node. Now, the problem is, in even if the name node, how can the name node be still performant? The second attempt name node does is it keeps all the metadata into the memory. While keeping a backup on the hard disk, it keeps all the metadata into the memory, which means that it can answer to you very quickly and never becomes the bottleneck. Okay, so still, name node will be can go down and will hurt the whole process. For exactly same reason, something called secondary name node was invented. So secondary name node remains as a backup of name node, sort of a standby of name node. Name node keeps on informing about all the new metadata which is coming in, as well as all the data nodes inform name node as well as secondary name node about the possible changes. So effectively, name node has got a mirror copy of itself in the form of secondary name node, or some people call it a backup name node. Other design by other non Apache guys is called backup name node. Backup name node is always readily available, just like name node. The moment name node goes down, you can swap it with with the secondary name node. Okay. Though the secondary name node, backup name node is not are not really high availability in the sense that they don't switch automatically, but that is fairly tolerable. And moreover, people are working on making it highly available, in the sense that in case name node goes down, it should automatically swap with secondary name node. Okay. All right. So Syam and Sanjay, have I answered your question? Okay. So Syam's question further is, for performance needs, are there situations where there are multiple name nodes and load balancing between the name nodes are done? So there is only single name node at any point of time. The reason behind having single name node is for consistency. Okay. The file system is designed to be heavily consistent, as in all the users see exactly same data. They don't see different data at the same time. Okay. If you have multiple machines, and even if out of multiple machines you have primary secondary kind of architecture where all the users are writing to primary and all the readers are reading from secondary, and data is getting moved from primary to secondary, the chances are there that the readers will read the older data, and writers, there will be a disconnect between readers and writers. So therefore, to stay heavily consistent, strongly consistent, HDFS or Hadoop has kept the design this way. All right, great. Now, this is the typical architecture as I explained to you just now. HDFS client, when they want to write the data, you by the way of Hadoop distributed file system or output stream, what they do is they go to first, a client goes to name node and tells him that, hey, I want to write this particular movie, and name node tells that we have got these data nodes, can you write your first block on this data node, your second block on this data node, and your third block on this data node, and so on. So it informs the client that, hey, these are the things you need to do, and once you are done, please come back and inform me. So HDFS client does exactly that. All right. So after following that instruction, client goes to data node, starts writing it, and this data node starts replicating each block. So client, as in client library, will slice the file and will start writing first block onto data node, second block, first, second, third, whatever blocks are there, and this data node will start replicating it onto other machines. Okay. So this way, the blocks are distributed by data nodes themselves, not the name node. Okay. And once client finishes the work with the data node, it writes back to the name node saying, I am done. Similar is the case with reads. HDFS client comes to name node, says, hey, can you tell me where the block locations for this particular file is? This particular file exists in this folder. Can you tell me the location of this? And name node gives the location of each block as they are located inside data node. And then client goes to each of these data nodes and start reading. Okay. And name node also knows that which data nodes are more busy, and accordingly it gives the preferred locations of data node, so that all the requests of the blocks do not go to a single data node, right? So that is how a file system is designed. Now there are other components built on top of file system. Okay, so these are the other components as of Hadoop, which we will be discussing in this session. And in addition to these components, we will also be discussing few more things such as Zookeeper, and we will also discuss something called Storm. So, so we have, as part of Hadoop ecosystem, we have a file system. File system provides you a beautiful file system, just like your your Windows file system or Unix file system. It's a network file system, as in you can write to it from any machine, and it will run parallelly on multiple machines by the way of admin node and data nodes. And everybody else depends on Hadoop distributed file system. So starting with something called Yarn. Yarn is your compute engine. By the way of Yarn, instruct your programs negotiate to get the computation done on multiple machines. Okay. Also, when the computation happens, the computation goes to, say you wrote a program to compute average. So this function average will go to each individual machine, and the average will be computed on each machine. So this computation distribution across the cluster is done via yarn. In our typical architecture, what we used to do is we read data from database, we do some computation, then put the results back into database. So that kind of computation is not something which is done here. Mostly, we divide our logic onto multiple machines by the way of yarn. And dividing the logic is a very tricky thing. That is why the frameworks like MapReduce and Spark are built for you. Okay, these are high level paradigms which make it very easy to divide your computation onto multiple machines, so that your work gets done by multiple computers simultaneously without you having to do all kind of engineering and mechanics by yourself. Yarn and MapReduce and Spark, they do that kind of job for you. Okay. Now there is something called HBase. HBase is a humongous database, as in if you have to store billion rows by billion columns, so probably HBase is one of the solutions. Alternatives to HBase are your Cassandra and MongoDB, CouchDB, and others. Okay. Now HBase is more like a data store. It gives you key value pair storage, which looks like a database. It gives you a very, very simple way of writing to the database. It doesn't provide you any kind of query. Okay. And when you have to do a lot of computation on top of HBase, you need a paradigm like MapReduce to do all of that. All right. So HBase is your database. We also call such kind of databases as NoSQL database. We will talk about NoSQL database in session number 6, and we'll go into more details. Now, for every problem, you cannot keep on programming MapReduce or programming in Spark. Okay. For very obvious problem which can be solved using SQL, Hadoop provides you Hive. To Hive, you give an SQL saying select star from my table where data is this much. And this query gets divided magically into smaller computational units and divided across the cluster. Rather than one computer solving your problem, the multiple computers will solve your problem and data will be gathered and given to you. That is the magic performed by Hive for you. Okay. So you will simply write your standard SQL query, and the whole query is going to get distributed under the hood magically by Hadoop. So that is Hive. Now, there's something called Pig Latin. Pig Latin essentially distributes exactly the same way what Hive does. Okay, just that instead of having SQL interface, it has got a new language. Okay, since SQL was not really designed for distributed computing, there were few things which SQL does not provide. The Pig does that for you. Okay. Pig is a very simple SQL-like language. Now, these are all great. These are all standard way of cleansing data and standard way of doing basic analytics. If you have to do the real magic, such as recommendation, sentiment analysis, grouping the items together, do machine learning, then in those cases you use Mahout or you use MLlib. MLlib runs on top of Spark, while Mahout used to run on top of MapReduce. Okay, so Mahout is your collection of standard algorithms for various kinds of data science job. Okay, such as recommendation, machine learning, and other things. Now, out of all of this, there would be a circumstance when you want to move the data from relational database to file system or to HBase or to Hive. In those cases, you will use Scoop to import and export a structured data from a database. But in case you have to move the unstructured data, say Apache logs, from all of your web servers continuously and immediately, then you will use a thing like Flume. Also, in case you are downloading data from a web crawler or from any other way, you will use Flume to continuously push that data to HDFS or HBase. It will be up to you absolutely. All right. So this is the ecosystem. Okay. Syam's question is, what is a typical HDFS client? So there are many HDFS clients. One is basically at the basic version of HDFS client is in the form of a Java library. Okay. Now, a typical client is a command line called Hadoop. Using Hadoop command line, you can do a lot of things quickly. The other client, a higher level client, is web interface. I'll show you this part quickly. Now we have got Hadoop. Now this. All right. So I've gone to a wrong place. So this is my our Cloud Labs control. It shows me the statistics about all machines running parallelly, and this is my HDFS. I'll show you my file system. Using this tool, this is also a typical HDFS client. All right. So for you, these are our students' data. So for you, for a user of a file server, this looks like a typical file system, right? But under the hood, whole thing has been running on multiple computers. Okay, under the hood, whole thing has been running using multiple computers. So you can see this. The data is here. So folder and lot of things are stored that way. Okay. So you do not have to worry about the mechanics of data node and other things. Here, if you see my HDFS, it shows you that 3 out of 4 data nodes are alive. Okay. So one data node is dead, which means this has been done for experimentation purpose, whether the data nodes are being copied or not. So it says that these are the missing blocks from one of the data nodes. Okay. So basically, even though there are the files are stored on multiple file system, multiple machines, multiple devices, you see as a uniform uniform data across whole cluster. You don't have to worry about the details. Okay. Okay. Prabhat's question is, could there be a consistency issues between data nodes? So there could be definitely. So what happens is when you are having multiple data nodes, so the consistency is heavily guarded by name node. Okay. So if a writer is coming to write the same file which is being written by an existing writer, the name node will stop them and will give an error saying this file is being written by somebody else. Okay. So the other kind of consistency issues could be that individual data node got corrupted. There are some bad blocks in the hard drive of one data node. So one block got corrupted. In those cases, in those cases, the checksum will be different for a particular data node. When the particular file is being retrieved from a data node, the checksum will be different from the actual checksum which has been saved, while checksum is a signature of the data. Okay, it's very difficult to forge a signature of the data, and immediately that block will be discarded and other replication will be used. Okay, so was I able to answer your question, Prabhat? Now, what is machine learning? Prabhat's question is, what is machine learning? Machine learning is a form of training the computers to do stuff automatically. Okay, so that is machine learning. Using machine learning, you can basically train a computer to do the rest of the job automatically. Okay. And the most simplest form of machine learning is creating an equation. If you are given four data points and you're told that these are the four data points, so for this value of y, this is the x value. For this value of y, this is the x value. And for this value of y, this is the x value. Now, next question, after you have given this data to the computer program, you will ask the computer what is the value of x for this value of y. And it will do the interpolation and extrapolation automatically. So this is the machine learning in the most basic form. Okay. And the life gets complicated when you have more variable and you have more kind of graphs. If it's a straight line, the relation between y and x is straight line, it's very good. But if you have many variables and many variables, and you have millions of variables and millions of values, then it becomes difficult to emulate using the graph fitting algorithms. That's when the machine learning becomes complex. All right. So that is the machine learning. This is what we call machine learning. First we trained the machine for giving, for this value of y, this is the x value, for this value of y, this is the x value, and at the end of it, after we have trained and we have given say 50 points of y and x, then we can start asking the computer saying, can you tell me the value of x if value of y is this much? All right, good. So was I able to explain what is machine learning? So this is the most common form of machine learning which we did earlier. These algorithms of graph fitting, extrapolation, interpolation have become more and more sophisticated, and sometimes we use neural networks, a layer or a simulation of the neural network to produce the results instead of standard graph fitting. Okay. So, machine learning is a composition term in which there are many algorithms for doing the guesswork. Those algorithms can be statistical, can be based on AI, can be based on neural network. So those are the things. All right. So that is one thing. All right. Now we have got something called Cloud Labs. As I gave you a quick demo, this is basically our Cloud Labs where you will be free to do all kind of experimentations. Okay, you will be free to do all kinds of experimentations continuously. All right. So I've already discussed. So any doubts about our Cloud Labs? We will give you the access to Cloud Labs for 50 days. And in case you want further access, we will provide you the further access also. But you have to inform us at least 1 week before you want access to Cloud Labs. Now, those who have already signed up the course, they can finish the quiz based on today's exercise. They can go through the quiz. There are around 50 questions based on today's session, and there are you go through the admin console because you must have got the login password to Cloud Labs, and you can go to the hue for controlling various tools. Also, those who have not signed up, they can sign up for second class onwards from 22nd February, which is going to be from morning 8 a.m. onwards. And if you are going for evening class, second class is starting from 1st March. Basically, the first class, exactly the same what we have discussed today, will start on 28th February, and so on. Why did you name Ambari console Ambari? So Rupam, this is Rupam's question. So it's not our name. We are just using a cloud provisioning tool called Ambari from Apache. Okay. I don't know why they use it. I'll have to see the taxonomy part of it. Why, what's in the name? Okay. The only name we have coined is for our Cloud Labs. Cloud Labs is our trademark and our keyword. And because there are I mean, although everybody in the industry now, everybody is using Cloud Labs as the term we coined. Okay, so you can sign up for our course. The this discount might be closed from Monday onwards. It has got 25% discount as an early bird. From Monday onwards, which is tomorrow, this discount may not be available. Okay, and total sessions are 33 hours, 3 hours into 11 classes. It'll be every Saturday, Sunday. On Saturday there'll be 3 hours, on Sunday there'll be 3 hours class, which means every weekend you'll have 6 hours, and hence it will take 5.5 weekends to finish the course. Okay, so this price includes everything: Cloud Lab support as well as taxes. Okay. Yes, you will all get the presentation, this PPT. We'll send it after the recording is uploaded onto our servers. We'll send you a recording and presentation in the email. All right. So you can sign up from our website itself. If you go to No Big Data, from there you can enroll for whichever batch you want to enroll for. All right. So feel free to get in touch with us if you have any question. Okay. So every class is recorded. Okay. Every class is recorded. So that is so Shyam's question is, what if I miss a class? Is there a way to catch up before the next session? Every session we record it and make it available in LMS. You can go to my course and look at the past all the classes, and you can get it. Okay. So either you miss a class or you want to revise your concept, this recording is going to be available for lifelong. Okay. The access to our learning management system will be for lifelong. Okay, and so therefore nothing to worry on those parts. All right, so feel free to get in touch with me if you have any doubts, any questions. Also, you can start contributing, you can start asking your questions even if you are not signed up as a student with us in our forum. Okay, we'll try our best to answer your question. There are a lot of people who keep on answering question on the forum. You can go to knowbigdata.com/forum. All right, any other questions to me? Are there going to be multiple instructors? So for this session, big data and Hadoop, I am going to be the instructor for this session for the next upcoming both the classes. Okay, in future I don't know. Okay, we have some people who are a little better than me. They might take up after the March class. Okay, okay. So I was trying to Sham's question that are there going to be multiple instructors? So right now I am the one who is owning this particular course, but for Node.js and MongoDB there are other instructors. All right. Any other questions for me? Okay. So a detail. Okay. Thank you, Prabhat, for that question. All right. So here are the details. So Prabhat's question is there a detail of 5.5 weeks program? So 5.5 weeks looks like this. These are the 11 sessions, and the detail. Let me also tell you. Say for example, if you're signing up for 28th February, so first session will be on 28th February, then second session will be the second session will be on 1st March, and third session will be on 7th March, then 8th March, and so on. Okay, and these are the course which we are going to cover, starting with MapReduce, advanced MapReduce testing, and so on. Okay, and the details are available on our website also. If you go into here, the website, the curriculum is available over here of all the 11 sessions. Okay, all right. Any other questions? Are there specific course material and references shared? Yes. So for each session, whatever whatever course material we have is generally sufficient, but there are cases when the further references are required. Those are mentioned on the LMS itself. Okay. So Prabhat's question is, would there be a case study project to practice the concept learned? Yes. So there will be two case study and course project which we are going to talk about. One is how to build a recommender. Recommender means a recommendation engine, or in other words, we call it collaborative filtering. Okay. It essentially means given history of the user, all the users, can we give them a recommendation? Okay, so one is that second uh, project which we are going to deal with is the sentiment analysis, understanding the sentiment of the people using Twitter data. So those are the two case studies which we'll cover in this course. So Rakesh's question is, any certification exam available after this course? So the general certification exam does not cover all these aspects. General certification only cover up to fifth, up to the Pig Latin. There is a certification exam by Cloudera, and okay, so Our course is basically heavily tuned to any certification exam. Okay. So Shyam, should I repeat the answer? Are you able to hear now? Okay. So should I repeat your question? Your question was, are there specific course material and references? All right. You can watch the video to get the answer anyway. All right. Any other questions for me? Feel free to drop me an email. My email ID, my phone number is mentioned in the slide on the last page here. This is our email ID, reach us at no big data. If you reply at reach us at no big data, somebody else who is from administration side can answer to your normal administration questions, while the technical questions I will reply. And you can also call me. This is my personal number. And if you have a general query, you can call us on this number as well. So either number is fine. All right. Any other questions for me? All right. So any other questions for me? Okay. Naresh, can you hear me now? There was some connectivity issue for last 1 minute. Okay. So how can I download this recorded session and PPT? Rakesh, you will receive an email from our side with the recorded video and the PPT. All right. Feel free to blog about us. Feel free to, uh, blog with the key points which you have learned today. As well, in case you want to sign up for the course, feel free to connect with us. Right. And also you can participate on, you can ask your question on our forum, so that either us or any of our student or our the other trainers will reply. Okay. All right then, thank you very much. Have a good day ahead. Okay then, bye. Have a good day. I hope you like the session. Thank you, Sham. I'm happy that you like the session. Bye bye. Have a good day. Feel free to get in touch in case you have any question. All right. Yeah. So thank you, Sham, that you found the basics covered really well. The objective of this session was that whether you want to take up a session or not want to take up a further session, this whole introduction will give you the clarity. Because if you are from sales background, you may not necessarily like this session, like the full course. But this first session will suffice for you. Okay. So have a good day. Bye bye. Get in touch if you have any questions.